So yesterday we covered the calculation of signal timing. Okay, the yellow, the all red time, the equations for it, the loss times. We did not calculate them, but there were some values which we discussed. And then we moved on to the critical volume, how to combine them, how to compare them. And we did one example where we calculated the cycle length, and after the cycle length, we calculated the green time. So just one thing which is from the last lecture. So the green time is calculated like this, and this is what we did yesterday. Okay, there is one step which we did not do. Okay, because we have not calculated the yellow and all red time, but the loss time was given. You can still do it. Okay, so for example, we calculated the green time for each phase for this diagram. Okay, so after you calculate this green time, this is not the green time of light, the time of the green light. This is the effective green time, okay, without the lost time. Some of the yellow time is lost time, some of the green time is lost time. So this effective green time is not the same as the the green light time. So if you want to calculate the green light time, the time for which you will see the green light, what happened? Okay, the time for which you will see the green light. So you have to take the effective green time, okay, and you will add the lost time. Okay, you will sorry, effective green time equals to the green light time plus yellow plus all red minus the lost time. Okay, so this is how you convert the effective green time to a green light time. Okay, the actual green time. So there's an actual green time, there's an effective green time. Effective one is the small one, the one which we calculated in the example yesterday. To convert this to the actual green time, you have to use this equation. Okay, so as you can see, I need the yellow time and the all red time, and I need the lost time as well. So this is an extra step which we did not do because we did not calculate for this example the yellow and the all red time. Okay, but this is something which I showed you in the last topic, this equation. So I just wanted to revise it when we have already calculated the effective green time. Moving on to the last step of signal design, which is the pedestrian check. Once you design the signal, we need to check if the signal timing is enough for the pedestrians or not. So it has 3 steps. The last step has 3 tasks, 3 activities. The first activity is to calculate the pedestrian required time, how much time the pedestrian requires. Okay, so we will start with that. Our GPI is the pedestrian required time. GP is the pedestrian required time, and I is for a specific phase because pedestrians are moving in different directions. So all directions will not have the same amount of time. All directions will not have the same amount of time. So you can see GP has, so I refers to the phase. So if you have 3 phases, I will be phase 1, phase 2, phase 3. So GP has GP has 2 components. The first one is called as minimum pedestrian walking time. Okay, this one is minimum pedestrian walking time. How to get it? We have some recommended values from the standards. Okay, so, and these values depend upon the area and the pedestrian volume. Pedestrian volume is higher, area is busy, you give more time. Pedestrian volume is less, the area is less busy, you will give less time. But you can see it goes from 15 seconds to 4 seconds. Okay, so this is the first component. You can calculate it from here. Okay, and if you feel that there are too many old pedestrians in the traffic, you can calculate the minimum time yourself as well by taking the width of the intersection divided by 3 feet per second. So for old pedestrians, the speed is taken as 3 feet per second. So if there are too many old pedestrians on your location, you can calculate the minimum time yourself by taking the width of the intersection divided by the speed of pedestrians 3 feet per second. Okay, old pedestrians. Now for the other thing, the other component, which is called as pedestrian crossing time. Pedestrian crossing time is calculated like I just told you for the old pedestrians, but now the speed will be higher. Okay, so PCI is the length of the intersection divided by speed of the pedestrians. Okay, so for older pedestrians, if you are taking 3 here, then for normal pedestrians, it will be more than 3. Okay, something. You can do your own studies to find out what is the average speed of pedestrians in your area. Okay, so there are two components for pedestrian required time. One is the minimum green time, the other one is the crossing time. Minimum green time you can calculate from this table. If the older pedestrians are not too many, if there are too many, then you will calculate it by using the speed of 3 feet per second. Okay, and the length of the intersection. If and in any case, the other part of pedestrian required time will be calculated using this PC, and PC means the crossing time, length of the intersection divided by the speed of the pedestrians. Okay. Now the second step is, so this is the first step. First step, you find out GP. The first step is to find out GP. The second step is I will compare this GP with the signal timing I have. Remember, we have already designed the signal. In the previous steps, we have covered the steps for designing the signal. So now you will compare GP with the signal timing. You have 3 criteria. You can apply one of these 3 criteria. Okay, you can apply one of these 3 criteria. Okay, the first criteria, all of them are given here. All of them are given here. So this is the first criteria, option 1, option 2, option 3. Okay. So what are these criteria? In the first one, you are saying GP equals to green, yellow, and all red, all 3 of them. Okay, GP is at least equal to green, yellow, and all red. So this is in the first criteria, the minimum for pedestrian time is green, yellow, and all red. Now the problem with this approach is after all red, the next signal will become green immediately. After all red, the next signal will become green immediately. So there is, for example, something happened to the pedestrian. The pedestrian was crossing the street and he fell down. So now he needs maybe 3 seconds extra to get up and start moving again. So in the first criteria, there is no extra seconds for him. So the accuracy level must be very high for you to design according to this criteria. If you go to the second option, you have pedestrian time at least equal to green and yellow only. Now we know that after green and yellow, we will have all red. Okay, so consider the first case. Pedestrian was crossing, he fell down. Now he needs maybe 1 second extra to get up and start moving again. So that 1 second extra is available for him from the all red time. Okay, that 1 second is available for him from the all red time. All red is, let's say, 2 seconds. So even if your calculation is off by 2 seconds, if you miscalculated by 2 seconds, or pedestrian because of some reason needs 2 seconds extra, he can still have it from the all red time. Okay, so you have some margin of safety here. And the third one has a greater margin of safety where you say pedestrian time is at least equal to the green time only. So I know after green time, this signal will have yellow and this signal will have all red. So until all red, the pedestrian is still safe. So even if my calculations were not so accurate, I'm still giving him some margin to go from one place to the other. That margin is in the yellow and all red. Okay, so you can see when we go from option 1 to option 3, my margin is increasing. The margin I'm giving to the pedestrians to cross is increasing. In the first case, it was nothing. Okay, but all 3 of them are technically correct. Okay, all 3 of them. Nobody can say no, I will never take the first option. Even if somebody takes the first option, he is correct. There is no problem with that. Okay. Before I move to the example, anybody have any questions? Are there any questions from anyone? Yeah, if somebody wants to join from section 3, go ahead, no problem, I don't mind. Are there any other questions or any other problems? Okay. So now this is an example. We have a signal with two phases. Okay, signal has two phases. Okay, so if I go here, I is 1 and 2. Okay, I is 1 and 2. So I have to check the pedestrian timing for both phase 1 and phase 2. Now the green, yellow, and all red time is given for each phase. Lost time is given for each phase. And the pedestrian required time is also given for each phase. So they already did this calculation for us. Okay, they already did the calculation and GPs are given here. Okay, so for phase A, the pedestrian time is 20 seconds, and for phase B is 20 seconds, and they are going for the first option. They are going for the first option. Remember, this is capital Y. This is capital Y. So capital Y is considered yellow and all red both. If it is small y, it's yellow only. If it is capital Y, it's yellow and all red both. Okay. So that's why I'm saying they are going for the first option. Capital G plus capital Y means green plus yellow plus all red. Okay, so they are going for the first option. Now what they are saying is check the pedestrian time, and if any adjustment is required, then do it. Okay, so up till now we have seen how to calculate the pedestrian time, step 1, how to check the pedestrian time, step 2, step 3 is adjust the signal time if required, which we will see in this example. Okay, first of all, let us check. Now, if you look at phase A, green plus yellow plus all red, 40 plus 3 plus 2, total is 45. Okay, okay, so the total is 45. Okay, so for phase A, I have 45 seconds available, and the pedestrian time is only 20 seconds. Okay, so my actual green time is more than GP, no problem. Okay, here the actual green time is more than GP, so there's no problem. For phase B, okay, green is 15, then plus 3 plus 2. Okay, so it is 20 seconds. Okay, and it is less than the pedestrian time, which is 30 seconds. Okay, so adjustment is required in phase B here. Adjustment is required in phase B. Okay, how to do the adjustment? For doing the adjustment, first of all, we will calculate the effective green time. Okay, how to calculate the effective green time? I wrote it here. Okay, and let me show it here as well. So effective green, so actual green time equals, effective green time equals actual green time plus yellow, small y, plus all red minus lost time. Okay, so if I'm doing it for phase B, then it will be, phase A, it will be 40 plus 3 plus 2 minus lost time, which is 5. Okay, so 40 seconds again. Plus 3 plus 2 minus 5, 40. Okay, if I do the same thing for phase B, if I do the same thing for phase B, I'll get 15 seconds. Okay, so effective green time for phase A is 50. Effective green time for phase A is 40. For B, it is 15, 1-5. Okay, and how do we get it? We did it like this. Okay, now I want the phase B time to be equal to the pedestrian time, right? The phase B time should be equal to the pedestrian time at least. Okay, pedestrian time is 30 seconds. Okay, pedestrian time is 30 seconds. So phase B time should also be at least 30 seconds. Okay, it was 20. Now I want to make it 30. Okay, so GP plus Y should be equal to 30 seconds. Okay, GP plus Y should be equal to 30 seconds. Okay, now what I will do, let me write it here. So now I will recalculate the effective green time for phase B using this value, because I want to achieve this value, right? Okay, I want to make it 30 seconds. So how did I get 25 here? GB plus Y should be equal to 30. Okay, so this is 30 minus lost time. Okay, lost time is given 5 seconds. This is how I got 25. Okay, now keep one thing in mind. Again, Y means small y plus AR. Y means, capital Y means small y plus AR. Okay, so yellow plus all red, all included. Okay, and we are taking the first criteria, this one, which says pedestrian time should be at least equal to green plus yellow plus all red. Okay, the pedestrian time is 30. So green plus yellow and all red all should be at least equal to 30. Okay, so effective green time is all this minus lost time. So all this should be equal to 30 minus lost time, which is 5 seconds. Okay, if anybody has any problem, please stop me and let me know. Anyone has any problem? Okay, I'll move on. What now you have to keep in mind, once you make changes in any one phase, the other phases should change in the same proportion. If you make, for example, 10% change in phase B, the other phases, whether there are 2 phases, 3 phases, 1 phase, whatever, it should also change with the same percentage, with the same proportion. Okay, why? Because otherwise you will disbalance the traffic. Okay, you will disbalance the traffic. Remember yesterday when we were calculating the signal timing, we were taking ratio of flow of one phase upon the total. So there's a balance. We are maintaining the balance. Okay, that the each phase, if you combine the flow of each phases, it will be equal to the total. So if you just change one phase, then you will not achieve this. You will, if you combine after changing only one phase, it will not be equal to total. Okay, so in the end, the total should remain 100%. Okay, agreed? The total should remain 100%. So if I'm going to make any change in phase B, I have to make the change in phase A as well. In this case, I hope only phase A. But if there were 2 other phases, I have to make the changes in those 2 as well. So whatever number of phases you have, one change will affect all of them. One change will affect all of them. How to make this change? First of all, I will calculate the cycle length. Okay, cycle length is summation of all phases. Cycle length is summation of all phases. So one phase equals to yellow plus green plus yellow plus all red. So the portion which I have highlighted here is phase A. Green of phase A, yellow phase A, all red of phase A. And this is for phase B. Okay, so phase A plus phase B. If there were 3 phases, I will add the third one as well. If there are 4 phases, I will add the fourth one as well. Okay, so this is my this is my old cycle length. Okay, I added both the phases. My old cycle length is 65. Okay, now I will recalculate my cycle length using the new timing of phase B. Okay, using the new timing of, remember I was taking here the old time of phase B. So now I'll take the new time of phase B to recalculate cycle length. So I will call it CN, new cycle length. Okay, new cycle length is what? 65, the old value of cycle length. Okay, multiply by the new time of phase B, effective green time. The new effective green time of phase B, which is 25. Divide by the divide by the total no sorry Let me just check. I'm missing something. Sorry for that. Yeah, okay, fine. Okay. So the new time of phase B upon the old time of phase B. Okay, so new cycle length equals to the, or and it's a ratio approach if you want to. Okay, if it is confusing you then. Okay, so new upon old cycle length equals to new upon old for phase B. Okay, new upon old for the cycle length is equal to new upon old of phase B. So this is the new of phase B and this is the old of phase B. And I'm taking the green time. I'm taking the green time. Okay, so can somebody give me the value of Cn here? How much is the value of Cn, the new cycle length? Yes. How much is Cn? So 25 upon 15 into 65. How much? How much is this? Yes.
108.3 دكتور.
108.3. Okay, 108.3 seconds. I told you yesterday as well, we round up the cycle length to the nearest 10 or 5 seconds. Okay, so we'll make it okay, we will make it 110 seconds. Okay, this is my cycle length. This is my total cycle length. Okay, now I will remember I want to calculate the time of phase A. Phase B, I already decided because of the pedestrian timing, it should be sorry, for 25 seconds. Okay, phase B already decided should be 25 seconds. So now I need to recalculate the time for phase B. Sorry, phase A. The new time for phase A. Okay, so what we will do is and again it should be in the same ratio. Okay, so the old time of phase, again I will use a ratio approach. I'll use a ratio approach. So G A dash, the new time of the new green time of A, divided by the old green time of A. No, sorry. The new green time of A divided by the total should be the new total. Okay, so the new total is, but I'm missing one step. Sorry for that. Okay, first of all, let us calculate the total green time, total effective green time. Okay, total effective green time is 110 seconds, which is the cycle length, minus the lost time. Lost time is 5 seconds for phase A, 5 seconds for phase B. So total lost time is 10 seconds. Okay, so I have 100 seconds available, total 100 seconds available. Okay, so the total new time is 100 seconds. Okay, now for phase A, new time of phase A upon new total, okay, equals to the old time of phase A divided by the old total. Okay, so the old total was 65 minus 10. Okay, because the lost time is still 5 seconds and 5 seconds. Okay, the lost time is still 5 seconds and 5 seconds. Okay, so the old time of phase A, I know it was 40. Okay, so how much is the new time for phase A?
0.73.
Huh?
0.73.
How? Did you multiply by 100?
It will be 73 then.
33, 40 upon 55 into 100.
No, 73 it will be.
73.
Yes.
Okay, let me recap. Sorry for what I did in the middle. Okay. First of all, pedestrian time was given for each phase. Okay. So first of all, I checked if the pedestrian time fulfills this requirement. For phase A, it fulfills the requirement. Pedestrian time is 20 and green plus yellow and all red is more than 20. No problem. Phase B, pedestrian time is 30. And if I add green and yellow and all red, it is less than 30. So phase B needs to be changed. How much it should be changed? It should be changed so that green and yellow and all red becomes equals to 30. So green and yellow and all red becomes equals to, where is it? This one. Okay, it should become equal to 30. So that means that effective green time for phase B equals to 25. Okay, so this is now the new effective green time for phase B. So we cannot change one phase and keep the other phases same because we want the total to be still 100%. All phases are divided in proportion, so we don't want to disturb the proportion. So I have to change the cycle length as well. So I calculated the old cycle length. Okay, so the new cycle length upon old cycle length equals to the new time of phase B upon the old time of phase B. So this will give me the new cycle length. From the new cycle length, I subtracted the total lost time, 5 seconds and 5 seconds for each phase. Total lost time is 100. Okay. From the old cycle length, I will do the same thing. 65 old cycle length minus 5 seconds, 5 seconds for the lost time. So this becomes 55. Okay. I will use the ratio approach. The new time of A, the new time of A upon the new total time equals to the old time of A upon the old total time. Okay. When I say total time, I mean the total green time, total effective green time, not the cycle length. You can do it with the cycle length as well. You will almost get the same answer. Okay, but we do it with the effective green time. Okay, so this gives me the new time of the new effective green time of phase A. Okay, now you can put these effective green time, this effective green time in this equation, and you can get the green actual green time, the capital G, because yellow and all red and TL are not changing. Okay, so this is the third activity in the pedestrian check. The first activity was this one, find out GP. Second activity is this one, check, which we also did it in this example as well. And the third activity is if the check does not satisfy, you change the signal timing, but you cannot do it for one phase only. You have to change the cycle length and the other phases as well to maintain the balance of the phases, to maintain the proportion of the phases. Okay. Anybody has any problem? It's all clear? Okay. So these are some examples again from both editions of the book. Okay, so go through them. We did not do many problems. If you have seen the last two problems today and the previous one, we did problems in which some part was already done, because you can see that even with some part already done, it takes a lot of time to explain and do it. So in the problems which we have done in this chapter, they were not complete. So I would advise you to look at these problems which are given in the book. So you may find more practice to do, okay? Because otherwise you may get confused if something is not given in the exam and so on and so forth. Okay. Okay, moving on to the, it's not a new topic, it's an old topic basically. It's a revision of what you have already covered in the highway course. Okay, so it should be easier for you. Okay. The chapter is about road users, vehicle and road characteristics. Okay, we are covering the basic concepts. So you can see basic concepts about road users and highways you have already covered. Okay, but it's part of the syllabus of the course. So we go through it in the end as a revision. And obviously it will help you and it will revise what you have done in this course as well. Okay, traffic system comprises of 5 components. Okay, people who are using the roads, call them road users. They could be drivers, pedestrians, passengers, bicyclists. Okay, anybody who is using the road in any capacity. Then we have vehicles. Vehicles can be commercial or private. Private means the cars which are used for private purposes. You use them for your own trips. Commercial vehicles are those vehicles which are hired by others to be used. For example, a taxi, for example, a truck. Okay, so these are commercial vehicles. We have taxis as well. Taxis are called semi-private. Taxis are considered as semi-private, but trucks and buses, they are considered as commercial. Then we have streets and highways, all types of roads, basically. The third component is all types of roads. Then we have control devices. We already finished the topic of control devices. Signal is that control device. And then we have discussed markings and signs and signals and all these things. So they are part of the traffic system. The last one is the environment. Environment includes anything which affects traffic, but it is not part of the first 4 components. Okay, anything which affects traffic, but not part of the first 4 components. For example, if you have a street light affects traffic, but it's not part of the first 4 components. A pedestrian bridge may affect traffic. It's not part of the first 4 components. The weather conditions, okay, they are again part of environment, but because they cannot be included in the other 4, and they have an effect on traffic. Okay, we will start the discussion with the first component, which is the road users. Road users means people, and people have a very wide range of characteristics. Okay, characteristics of people are not at the same level. Somebody is fast, somebody is slow, somebody has some other visual disability, they have problems, so mental disability and so on and so forth. Okay, so we want to cover most of the road user characteristics. We want to cover most of the road user characteristics. So we do not take an average value, because average will not cover most. Average will cover half. Average means in the middle, right? So average will cover half. We want to cover most of them. So most of them meaning that they have set a standard that you should cover at least 85% of the people. You should cover at least 85% of the people. So that's why we take 85th percentile as our design value. Now, if you are going for the highest value, if you are looking for the highest, for example, speed of the vehicle, the speed of the car, okay, I want to design for the high speed. High speed means 85th percentile, okay. But if I'm going for pedestrian crosswalk design or pedestrian signal design, I'm not looking for the highest speed. I'm looking for the lowest speed. Okay, so then I will take 15th percentile. Okay, you get the point? You cannot go for, so I will cover 85% of the pedestrians, because 85% of the pedestrians will be faster than this value. Okay, in case of cars, I want to cover 85%. So I want to cover the car which is 85% faster. Okay, or it's in the 85th list. It's in the 85th order in the cars which are faster, because fast car is the worst case. In case of pedestrian, slow pedestrian is the worst case. A person who is moving slowly is the worst case. Okay, so we see which one is the worst case, the highest one or the lowest one. If the highest one is the worst case, we'll take 85th percentile. If the lowest one is the worst case, we will take the 15th percentile. Okay, so we are taking the complementary. We call it complementary percentiles. 85th is a complementary of 15, right? 85 plus 15 is 100. So you have to see what is your worst case, the highest one or the lowest one. If the highest one is the worst case, we take 85th percentile. If the lowest one is the worst case, then we take the 15th percentile. Okay. For traffic engineering, we need a good understanding of the driver characteristics, because up till now, most of the vehicles are driven by drivers. Okay. Maybe near future, we will have driverless vehicles, automatic vehicles. Okay. But even those vehicles are designed for driver characteristics, what other people normally will expect. Okay. So we need to have understanding of the driver characteristics. Our aim is to provide enough information clearly to the driver so that he can act in a safe and proper manner. Okay, our aim is to provide sufficient enough information with enough time to the driver so he can act safely and properly. So I want the driver to be in a specific lane. So I should show him the marking with enough time to come into his lane. Okay. And I want the driver to stop. So I should show him the stop sign with enough distance and clearly so that he knows when to stop and he can stop properly. Okay, in getting the information and acting upon it, there are two characteristics which are very important. Okay, in receiving and acting on the information, there are two characteristics of the drivers which are very important. One is called as visual acuity and the other one is called as reaction process. Visual acuity means he is receiving the information by looking at it. He is receiving the information by looking at it. And reaction process means now he is thinking and acting on the information. So visual activity is receiving information. Reaction is thinking and acting on the information. And obviously, these two processes, they happen together. When you look at something, your mind starts to work. Okay. So you look at, for example, your close friend and you want to go and meet him, right? So you are already going towards him before you even think about it. Okay, so when you look at something, your mind starts to work. So these two activities, these two characteristics, they work together. They work together. Or you can say, if I cannot look at something, then it will take for me longer to decide and act and to do something about it. Okay, so these two work together. Okay, some other characteristics for drivers are also important. Why they are important? Because they affect his or her behavior, his or her driving. Okay, these are personality and psychology. Personality and psychology. Personality means what? His default characteristics. Okay, for example, age, experience, education. These are your default characteristics. They are part of your personality. Okay. The other one is psychology. Psychology means your state, your physical and mental state. Your physical and mental state. So somebody is very tired. Okay. So this is his psychology at the moment. He may not be paying attention right now. Somebody is very sick. Okay. So this could affect his driving, but this is not a permanent condition, right? So personality is something which is permanent. It is in you. Okay. Psychology is how you are at the time of driving and it changes. It changes. Okay. Now, the problem with psychology and personality is it is very hard to control and it is very hard to measure. So you can measure vision, you can measure reaction time, but you cannot measure somebody's personality and psychology. You cannot give a number to it. So how do we use it in our design? We cannot use it in the design. So what do? We make laws and regulations which force the driver to drive in a certain manner. Okay, so laws and regulations are there to make the driver follow the correct driving behavior. Okay, so this is to cancel the effect of personality and psychology. So somebody who is a young driver who has just started driving, he has to follow the same traffic rules. Okay, he will drive on the road in the same manner as someone who has 20 years of driving experience. So the effect of experience is cancelled out because of the traffic rules. Okay, and how do I make sure that the driver who's on the road knows all the rules at the time of licensing? So that's why for license we have the lectures, we have the classes, we have the test, and so on and so forth. Okay, so traffic rules and regulations are there to cancel the effect of any bad effect of personality and psychology. Obviously, if it's a good effect, somebody is very experienced, he is very fast, he is very quick, he is very strong, we want that. But other who are not so strong, not so fast, not so experienced, we want to bring them to the same level. So that's why we have traffic regulations. And to make sure everybody knows and follows the regulation, we have the licensing, we have the fines, and so on and so forth. Okay, this table provides a summary of visual acuity. Remember we said for drivers, two characteristics are important: visual acuity and reaction process. So now we are talking about the first one, okay, visual acuity. Let me go in the full screen mode. Okay, so different characteristics are mentioned, their description is mentioned, and their example is mentioned, how they are used in driving. So for example, accommodation. Okay, so when you're looking at things at different distances, your eyes need to refocus like the camera of your phone or like the normal camera. Okay, so this refocusing happens automatically. Alhamdulillah, all these things happen automatically. Okay, we are just looking at them. So while you're driving, you look at your speedometer, and then you look at the road, and then you look at a traffic sign which is 100 meters away. So when you're looking at all these things, your eyes need to refocus for the distance. Okay, so this is accommodation. This is called accommodation. Static visual acuity is your ability to see things in static condition. When you go for driving license, they do a test for you, the eye test, that is for static visual acuity. And obviously, without a static visual acuity, you cannot read the sign, you cannot see your car, you cannot even start your car. Okay, adaptation means to adjust in different light conditions. Okay, so you are coming out of your garage was covered, now you are in the bright sunlight. Okay, or you are driving in the evening, now it is getting darker, so your eyes need to adjust to the different light levels. Then we have angular movement. Angular movement means your eyes need to adjust to the horizontal field. Okay, so when you are looking at something, you from right to left. Okay, so this is the adjustment from right to left or left to right. Okay, adjustment of eyes in the horizontal plane, so we need this to judge the path of the vehicles which are crossing us, vehicles or pedestrians. A pedestrian is crossing, so he will be crossing from right to left or left to right, right? So your eyes need to see how fast they are, how far they are, and so on and so forth. So this comes under angular movement. Then we have movement in depth. Movement in depth helps you to judge the speed of objects which are coming to you, so not across you. Angular was across. This is coming towards you. Somebody is coming directly towards you from the front. Okay. So when somebody is, so you look at the moon looks very small, right? Why? Because so far. If I was close to the moon, I will see that it's very big. Okay. So the moon may look smaller than your hand because it's so far. Okay. Your hand is bigger because of the distance. So movement in depth, you look at the size of the object, and then you try to judge at what speed the object is coming towards you. The object is coming towards you, the size is getting bigger, right? So this is called movement in depth. Then we have color. Color is the ability to differentiate between different colors. Okay, so we are using different colors on signal, for example. If you cannot differentiate between different colors, how would you know what the signal is showing? Okay, then we have contrast sensitivity, meaning to differentiate between something, a color in the background, color in the foreground. Okay, color in the background and color in the foreground. So if I use blue color over white, can you see it properly? Can you read anything which is blue over white, and so on and so forth? This is called contrast sensitivity, and it will help you especially at night. When you're driving at night, everything is black, and then you see somebody who is wearing maybe blue color clothes and he's crossing you. So can you see him or not? So this contrast sensitivity will help you with that. Then we have depth perception. So we already talked about movement in depth, right? Movement in depth is about the speed, and depth perception is about distance. Again, the concept is same. Something is in front of you. Okay, measuring its speed is called movement in depth, or having an idea about its speed is called movement in depth, and having an idea about the distance is called depth perception. So while you're driving, you need both these things, right? You need to know both these things. How fast is this thing coming, and how far is it? So car in front of me brakes. Okay, so I need to have movement in depth to know that now it is actually slowing down. And then I need to have depth perception to know when should I brake. Should I brake or not? Should I just go to the other lane? So that's why depth perception is important. Then you have dynamic visual acuity. Dynamic visual acuity helps you to read things which are moving, or to read things when you are moving. It could be one of these things. Either the thing is moving or you are moving. Either the object is moving or you are moving. So you are standing on the side of the road and the car is moving. This is dynamic visual acuity. You are in the car and you are looking at the speed sign. This is again dynamic visual acuity, but the frame of reference is different. Okay. So you need both of them. I just gave you the example. Eye movement. Eye movement means changing the direction of your gaze. Okay. So gaze is your line of sight basically. Gaze is your line of sight. So how quickly you can change your line of sight from one point to the other. Okay. So when you're looking at the road, you look at the side, is there any pedestrian? You look in front of you, is the road is clear or not? Okay. So this, you are changing your gaze. Then we have, so this comes under eye movement. Then we have glare sensitivity. Glare sensitivity means glare is something related to adaptation. Adaptation is to adjust for minor changes in light. Glare is to adjust in very significant change in light. Okay. So for example, a car is coming in front of you and the full headlights are on. So there's something suddenly comes in front of you and you are blind for a few seconds. It happens, right? If you are in completely dark condition and somebody switches on the light, your eyes will take more time to adjust. So this is called glare sensitivity, when the light condition changes rapidly and very significantly. Okay. So glare sensitivity, then you need some more time to adjust. Then we have peripheral vision. Peripheral vision means to look at things which are on your sides, basically near your shoulders, okay, or in the line of your shoulders, okay. So in peripheral vision helps us to detect the speed of other cars and our cars. When we are driving, if you are on an open road, which has nothing on the sides, clear road, you will go faster and you will not feel it. Why? Because your peripheral vision is clear. Okay. But if I put you on a one lane road and I put barriers around you, will go slower, even if the road is clear in front of you, because your peripheral vision is blocked. Okay. So peripheral vision affects your speed. Then we have versions. The angle between the, you have two eyes, right? You have two eyes. So you may have seen some people, they have one eye, slightly tilted. Okay. So they have to tilt their head to see straight. Okay. So this is a blessing from God that our eyes, if you are looking straight, both our lines of sight are in the same alignment. Okay. So this is called as vergence. Okay. So if your vergence is not clear, okay, then you will have problems in changing the angle of your uh, line of sight. Okay. So you are looking at the dashboard, then you start looking at the road, you are changing the angle of your line of sight. So if your eyes are not properly aligned, then you will have a problem with that. Okay. So vergence helps you with that. Okay. So I'll stop here. So I'll be taking the attendance for section 2 only, because section 1 I have cancelled myself. So section 2 people, they should wait, and section 1, the other section can go. Okay. So I believe you guys are section 2. So people who are at 3 p.m.